Oh, good. All right, so multiple choice, number 5. Here we go. It says a projectile is fired straight. It says a projectile is fired straight upward from the Earth's surface with a speed that is half of the escape speed. So our initial velocity is 1/2 of the escape velocity. It says r is the radius of the Earth. The highest altitude reached, measured from the surface, is what? So I think to figure this out, we first of all need to figure out what the escape velocity is, right? Hey guys, can we? Please. So I gave you guys the equation for the escape velocity, right? I think there's some value though in you being able to know what that, like how to derive it, because it's quick. You ought to be able to derive it really quickly. And if I remember right, I don't think that it's on the equation sheet, is it? Does anybody know?
No, it's not.
It's not. Okay. So it's basically a one-step calculation. Okay? So how do we derive that escape velocity equation?
Didn't we do it in the video?
We did it in the video, but I just want to make sure that everybody processed it, because it should be a quick thing. What do you got?
I was gonna say that, like, you know, the total energies are gonna equal each other, so you can, like, kind of move them around, and you know they're gonna be, like, equal to each other.
Right.
Because it's like one's negative, or kinetic, or the potential energy is always negative.
Good.
So you just move it over, then you can, like,
Yeah, exactly. So the idea is when we fire it, the potential energy is G times the mass of the Earth times the mass of the thing over the radius of the Earth, right? Okay? We need that to be such that when we add our kinetic energy initially, what do we need to get? 0, right? Good? So we just set, oh, sorry, I forgot my negative sign here. So you just end up setting GMM over R equal to 1/2 mv squared and solve for V. Do you see what I mean? Is it clear why these have to add up to 0?
Yeah.
Okay. So if you solve this, you get V escape equals 2G capital M over R square root E. Yes?
So like, I thought of it a different way, because like the way we always thought like what's your energy initially and then your energy, like your final energy.
Okay.
And your energy initial when you're like on the Earth is the GMM over R.
This guy.
Yeah, because you're not moving. But then when you're like away from the Earth and you're gone, you just have kinetic energy. So like that's how I got that.
Gotcha.
So is that still like correct?
Yeah, I guess so, because you're basically saying you need to convert that kinetic energy to potential energy.
Yeah.
So yeah, that works. All right, so I haven't answered the question yet, but I just want to make sure that this is clear, that you guys know how to do this. So everybody's good? All right, so great. So how do we use that then to figure out how far my projectile is going to go? Well, so let's see. So what's happening then is my initial velocity in this problem is half of this, right? So it's 1/2 times 2gm over r. So that means my kinetic energy initially is going to be, there's got to be a shortcut way to do this, but since I'm not feeling well right now, I'm not processing. So is it going to be 1/4, I think? I don't know, let's just figure it out. So it's 1/2 m times this squared, right? So this squared is going to be 1/4 times g, oops, sorry, I forgot my 2gm over r. Everybody agree with that? So it gives you 2gm m over 4r, right? Oh, no, sorry. There we go. Gives you that, right? No, we're not done yet, but that's the kinetic energy we start with when we launch it. Does everybody agree with that?
Yeah.
All right. And then our gravitational potential energy initially is still this thing, right? Negative GMM over R, right? Follow? Now, when it's at its highest point, what's going to be true? The kinetic energy is going to be 0, right? So, what I need then is I need to solve an equation that says that my total energy at launch is equal to the total energy at its highest point. So basically, GMM over 4R minus, or technically I guess plus negative, right? GMM over R has got to equal my potential energy at that highest point, right? So that is going to be negative GMM over X or D or whatever you want to call that, the thing that we're looking for, right? And then solve for X. Follow? Any problems? So, I guess math-wise, I would get rid of all the GMMs, and this just becomes 1 over 4R minus 1 over R equals negative 1 over X. And then solve that. So, let's do this. Let's make this a 4 and this a 4. So you get negative 3 over 4R equals negative 1 over X. So X is 4/3 R. So is my answer 4/3 R? What's the question asking? It wants to know how far above the surface it is, right? So the surface is at 1 R, so you got to subtract out an R, right? So it leaves you with 1/3 R. Make sense? So these multiple choice questions, I've had a couple of you guys say, there's never any problems in the homework that don't have numbers. No numbers. Okay? Clear?
Yes.
All right, did I lose anybody anywhere in that process? Is there anything I need to clarify? We're good? Okie dokie. Oh, you need a second, Carla? Yeah, me too. Yeah, yeah. At least comment on it. Unrelated to anything, while I'm waiting for Carla to write this down, my son wrote a story about a raccoon the other day in school. And he used the descriptor, he said, the raccoon sneakily snuck up the tree. And I thought that was really funny. He did too. He was very proud of it. Sneakily snuck. Right? Isn't that? I was like, he thought it was very funny. All right, everybody good? All right. No, you're okay. I'm going to steal your pencil if you don't mind. There you go. There you go. Here I go. All right. Nextest, but not leastest. All right. So 8, 9, 14, and 18. 8, 9, 14, 8, 9, 14, 18. Okay, yeah.
On the end of that last one, did I write it down wrong or did you get 4/3 R?
So that's how far away from the center of the planet the thing will go.
Okay, so 1 R, so minus 1 R.
Minus 1 R is where you get the 1/3.
Okay, thank you.
Yep. All right, so real quick, a couple people asked about number 9. Couple people asked about number 9. I'm hoping that I have the right answer on there. So, is everybody cool with how I came up with this escape velocity equation? What does the capital M represent? The mass of the Earth or whatever planet thing you're trying to escape, right? Guys, please. Number 9 says neglecting air resistance, a 1 kilogram projectile has an escape velocity of about 11 kilometers a second at the surface of the Earth, which is true. The corresponding escape velocity for a 2 kilogram projectile is... Does this seem to depend on the mass of the projectile? No. If I remember back like at the beginning of the year when we did projectiles and I said, all right, you know, Roy throws a ball up in the air at 10 meters a second, how high will it go? Did I ever give you the mass of the ball? No. Because it's still going to be affected by gravity in the same way, right? Because the acceleration is proportional to the force, right? So at number 9, there's no math there. It's just, it's C. It's 11 meters a second because the mass doesn't matter. Clear?
Yeah.
All right. What's up? Go.
I said yeah.
Number 8, I don't know if I want to get too bogged down with it. It's basically just some algebra wizardry. I can't imagine there being anything that's that algebra-y on the test. So let me put that one on hold for a minute, because I know there was some stuff from 14.1 that we didn't get to yet. So let me talk about 14 and 18 real quick. And then I think I'd like to give you guys a little bit of time to work on the problems. Cool?
I'm 14.
I'm sorry?
I'm 14. I have a question, but I don't know if other people probably see it done. But I just have a question. So when you said the minimum distance and maximum distance, do we just like assume that those add together to equal C?
No. They add together to equal 2a. So let's talk real quick about ellipses, because you have to understand ellipses to do number, whatever I just said, 14. Oh, am I still about that?